Thank you very much. Thank you for the lovely introduction. It's great to be here tonight. I'm going to tell you about some of the work that I'm doing, both on planets and in a slightly strange way, which maybe some of you have heard of before, and if not, I'll introduce, linking them to the faint stellar remnants of stars like our own, known as these white dwarfs. So it's really great to be here because it makes me feel, takes me back because it's not that long ago. Yeah, only about 20 years since I was actually a student and I was part of ALZU, which is the exactly equivalent to this in Oxford, and we did exactly the same thing. I was there, sat there, inviting our speakers and organising things. So it's very, very nice to be here tonight. And of course, that doesn't work. Right, there we go. So white dwarfs. Now these are amazing stars. Most astronomers think they're totally boring, but I really, really love them. And our sun, in kind of 5 billion years' time, it's going to run out of hydrogen in its core. It will lose all of its outer layers, and the what's left behind will shrink down until it's about the same size of Earth. So that's like putting in something that is about the mass of this, about half the mass of the sun is left, and now you're going to put it into the size of Earth. So it's really, really dense, supported by electron degeneracy pressure. So the actual forces from the electrons are holding it together. And these stars are incredibly common in our galaxy. So white dwarfs are everywhere, but they're really quite faint because they're not very luminous anymore and there's not much we can see. But hopefully by the end of the day, I'm going to convince you that they are worth studying and that there are some really cool things we can find out from learning about white dwarfs. And that cool link is with planets. So I'm particularly interested in planets around other stars, so exoplanets, and the fact that we can use those to better understand not only our own solar system and the exciting planets that we have there, in fact, our own kind of existence on Earth and the origin of life itself. Exoplanets have become one of the really amazing ways of getting kind of an idea of how that might have happened in other systems, and was our system similar, was our planet different, and how can we learn about what happened here? How important is it in our solar system that we have not only the kind of rocky terrestrial planets like Venus and Mars and Mercury, but also these gas giants, Jupiter, and the role that maybe Jupiter played in the architecture of our system, controlling lots of the scattering of small bodies like asteroids and comets around our system. So, planets around other stars. So these are the kind of other worlds we're all trying to learn about and trying to understand. And this is a wonderful artist's impression of one of those worlds. And we are starting to discover more and more of those. So I wanted to kind of start from the beginning and talk about very, very exciting discovery of the first exoplanet, which was a Jupiter mass, or several Jupiter mass planet with 51 Pegb. And it was discovered in 1995, so over 20 years ago now, around a star similar to us. And importantly, actually, the discovery was made by Mayer and Kellos, and Kellos is now here as a professor in Cambridge. And so I first started thinking about exoplanets myself, actually, when I was at school. And I very much remember towards the end of my A-levels getting excited, what am I going to do next? And I went to a talk, and I vividly remember the professor putting up, and at the time there was maybe 12 or 14 exoplanets, just a dozen or so around other stars. And this was the exciting new thing where we could just see, and these planets were all totally different to our solar system. They were all very, very massive, several times the mass of Jupiter on kind of very, very short period orbits. So much, much closer than any planet we have in our solar system. And I thought these were really cool. But at the time I thought, well, there's 10 of them, 10 planets. What are we going to do with that? This is really not the most exciting thing. But wait another couple of years, and today, recently, exoplanet.org announced that we have more than 5,000 planets detected around other stars. So we've really revolutionized our understanding of these planetary systems, and we can get things that are now down to kind of being Earth mass, and even slightly smaller than Earth mass in some places. And we're pushing towards detecting things that are on kind of year orbital periods, rather like our own planet, rather than these kind of day or hour orbital periods that we started with. So exoplanets is a booming field. It's super, super exciting. And we're really trying to get to the bottom of what these planets truly like. So this video is rather old now, but I kind of like it because it just kind of illustrates how amazing the planets are. So this was after Kepler, which is a space mission. That's annoying, I can't talk. But so after Kepler was a space mission that was really, really good at detecting planets around other stars. And these are all of the exoplanets that were detected by Kepler. And what the kind of plots are showing is in the middle, there would be a star, there would be kind of dot here. And these are all the different planetary systems. Some of them are multiple, some of them have got 4 or 5 planets, some of them just 1 planet. Sometimes they're big, sometimes they're small. Sorry, I'm moving too much for the camera. Is that better? And I just think it's really fun to see actually how diverse those planetary systems are. And to kind of note, none of these, all of these planetary systems, every single one of them would fit inside of the orbit of Mercury in our solar system. So they're all really tiny and compact. And that's just because we couldn't wait long enough to get the long orbital periods like our own planets. Cool. Yeah, so I wanted to just kind of highlight the diversity of these planets. So this is an artist's impression of a hot Jupiter, and just to kind of get us to kind of think and imagine about these different worlds. So can you, like, kind of Jupiter is this big ball of gas in our solar system. It's at 5 astronomical units from the sun. It's quite cool and it's far away, whereas these hot Jupiters, they're sat at kind of 0.01 AU from their sun, and they're being irradiated. They're being affected by the magnetic field of the star, the kind of flares, everything. And so the conditions on those kind of planets are very, very extreme. And often, in many cases, these planets end up being tidally locked. So that the tidal forces from the same kind of things that would cause the tides on Earth from the moon, the tidal forces on the Jupiter from the star are sufficient that they lock the planet such that only one face of it is facing the sun. So the planet kind of orbits around, always seeing day on one side and always night on the other. And kind of moving forward in time, we're also getting planetary systems which are incredibly different to these as we move to lower and lower masses. So this was a discovery maybe a couple of years ago now, made by a team in Belgium, and it's called the TRAPPIST-1 planetary system. And this planetary system, I think, when you kind of said, if somebody said to you, what were you going to find out there? Isn't nature the kind of most beautiful thing you could possibly imagine? And then you see something where you're looking at the signals and suddenly they keep popping out, and there's 7 planets all doing this little dance around the star, and they all popped out of the transit timings, kind of photometry signals. And so this planetary system has these kind of 7 planets that are all around about Earth-sized, plus or minus a bit, but compared to our solar system, they fit down in here in these tiny little orbits. And the star that they're orbiting, instead of being a kind of big solar mass star like our sun, it's a tiny M dwarf, so kind of 1/10 of the mass of our sun, really, and quite faint. Okay, so let's get back to those white dwarfs then. So we know there are planets out there, that lots and lots of stars have them, and almost all of the stars that we know that do have planets, they're not going to stay as kind of main sequence stars like we know our sun forever. At some point, they're going to start evolving and they're going to run out of hydrogen in their core. They're going to do some successive layers of burning, depending on how massive they are. And at that point, they start to swell up and to become these giant stars. So those giant stars can be kind of up to maybe an AU in size. They are really, really big, very, very luminous. You can get kind of 10 to the 3 times the luminosity of the sun, 10 to the 4 times the luminosity of the sun during the giant branch. They're really incredibly luminous, really hot stars, really, really large. And that's because that outer envelope of that star actually is kind of almost becoming unbound. It's getting bigger and bigger. It's swelling from those large temperatures until at some point, actually, it just floats off. There's not enough gravity to keep it bound to the star. The radiative pressure from that really strong burning in the center is so strong that it floats off gently in this lovely planetary nebula. And these are the beautiful things that we see kind of all over the universe that make absolutely amazing pictures. And what's left behind in the center of this planetary nebula, this tiny little faint remnant collapses down on itself until what I was talking about is electron degeneracy pressure. So this pressure that's from the electrons themselves supports it, and you're left with this kind of faint white dwarf. Okay, so then we have some planets around these stars. What's going to happen to them? the big question. So I kind of like to illustrate this by thinking about our solar system, but we know that planetary systems around other stars are very different to our own solar system. But we at least know that our solar system, it has some kind of terrestrial planets, there's Venus and Earth, and they're on kind of year orbits. We've got some asteroids here in the asteroid belt, just between Mars and Jupiter, and then we've got these big gas giants out here, our ice giants, Uranus and Neptune, and then much, much further out the Kuiper belt full of comets. And so what's going to happen when our star becomes a red giant? Well, firstly, the star is going to start losing mass. It's going to blow away that material from the outer envelopes. And so as it does so, the pull of gravity on all those planets is less. And so the planets themselves are able to spiral outwards. They end up on much, much wider orbits. All these planets are kind of spiraling outwards. But at the same time, the star got so big that Mercury went inside of its envelope. It's totally gone. Venus went inside the envelope and is most likely totally gone. And Earth is just on the edge where the jury's out, depending on whose stellar model you want to use, as to whether or not Earth goes inside and survives or not. So when you lose that envelope, you get left behind this white dwarf sun, which is now really, really tiny. And suddenly you've got this outer planetary system that is huge. It's expanded by a factor of 2 or 3. And now there's a big gap between anything in this planetary system and this tiny little white dwarf sun. But what has also happened when that star lost mass was that Jupiter sat here with a load of asteroids. Suddenly the influence of Jupiter on those asteroids grew. And that's because now there's not as much mass in the center. So when we were our solar system, we were nice and stable, and Jupiter was kind of in some kind of equilibrium with the asteroids here, and they weren't being scattered. But when we lost mass, suddenly the influence of Jupiter grows because the total mass in the center of the system has gone down. And that means that the asteroids and the Kuiper objects as well actually here start being scattered around. And this is really, really important because essentially this leads to the production of a whole load of things that are like comets, basically. Some of them get flung out of the system, but some of them get flung inwards. And just like we have kind of comets in our solar system that we're able to see from their tails when they kind of come close to the sun, these asteroids, if they get anywhere near this white dwarf, so within about 200 white dwarf radii of that white dwarf, the gravity is so strong, because that white dwarf now has the mass of the sun and something the size of the Earth. The gravity is so strong that those asteroids can no longer stay as a big 500-kilometer asteroid, 200-kilometer asteroid. Instead, the tidal forces shred them to pieces and they get torn to become this kind of dusty material around this white dwarf. And this is where the secret of using white dwarfs to study exoplanets comes in. Yeah, so I forgot I had a cartoon to kind of show us the kind of what's going on. So if we start with our kind of stable planetary system here, there's the sun, maybe this is Mars and Jupiter and some planets, and they're all on nice stable orbits before the star loses mass. Then the star loses mass, and the influence of these planets over each other grows because the stellar mass level is gone, and you scatter things onto chaotic orbits, so it can go totally crazy. And most of them will get ejected, but occasionally some things get scattered really, really close in, and it's those ones that we really care about. Because it's those asteroids that are then torn apart by those strong tidal forces close to that white dwarf. And they're the ones that actually the material from those asteroids ends up in the atmosphere of the white dwarf. You end up with this kind of some kind of accretion disk, and this material from that torn off asteroids enters the atmosphere of the white dwarf. And what's really neat is that we're able to observe and detect this process happen. And that's because of the key thing I said about white dwarfs. So we now got something the mass of the sun in something the size of the Earth. So the gravity is super strong. And that's really, really important because it means that everything is sinking downwards. So the gravity is incredibly strong. And so although white dwarfs do have these very thin layer of gas around them, maybe 50 to 100 kilometers thick, that gas is only going to contain hydrogen and helium. Anything that was in that was what as astronomers we call a metal, so things like magnesium, calcium, and iron, is going to sink into that core out of sight very quickly just because of the strong gravity. And the same if you add anything into the top of that atmosphere. So we're talking about these asteroids, which are now going to be added into this atmosphere. They're going to sink through that atmosphere, rather like throwing a rock into a pond, and they're going to sink out of sight. But what is neat is that we're able to catch some of these asteroids before they sink totally out of sight. And we're able to see them in the spectrum of the white dwarfs. So this is kind of one of these spectra. So it's looking at how bright the white dwarf is as a function of the wavelength. And in here, we can kind of pull out different lines that belong to different species, like iron and manganese, in this case, carbon. And these are all from material that's entered the atmosphere of the white dwarf. So I put in this slide to kind of explain a bit about the spectra. So spectra are a really neat way of kind of learning about what's inside of the atmosphere of a star. And so I kind of always see it as kind of a fingerprint. Like we all have a unique fingerprint, and so does every kind of element that we have in the universe. And depending on the ionization state of those elements, this fingerprint's different. So if we're looking at different kind of colors or different wavelengths, we see certain lines that are absorbed by those elements in the atmosphere. So the light is coming from the star on its way out. The iron in the atmosphere is going to grab it, but only at these certain wavelengths. And so by looking for those kind of fingerprints, we can pull out to say there was definitely iron here, and there was definitely calcium here, and even how much there was. Yeah, so this was kind of illustrating that again. So that's the spectrum from the star, the light's coming out, and it's being absorbed by different things along the way. And that gives us the absorption lines that we can see in the atmosphere of this white dwarf. And so these spectra are actually really, really powerful, because what we're seeing is the iron and the manganese and the carbon that was in that asteroid that went into the atmosphere of that white dwarf. And so from this, we're actually able to deduce what that asteroid was made from. And so this can actually tell us what asteroids around other stars, what elements they contain, and in what ratios they are to each other. And so this is another example. I seem to have lost my axes, but never mind. This is flux from the star, so it's how bright it is as a function of wavelength. And again, this is kind of emission from the white dwarf, and what we expect to see here is just hydrogen and helium. And instead, these are all the kind of lines that we see from things like iron, magnesium, titanium, even here, chromium. And these are all the elements that were in the asteroid or the comet that entered the atmosphere of that white dwarf. And so this is really, really cool, because we go back to our timeline where we were thinking about when we first started finding exoplanets, and the fact that I was a little bit disappointed at school that there was only 10 of them. Actually, that we were missing a few things. So we were actually missing these white dwarfs. So this is Van Maanen star, a star that was as a white dwarf, and it was actually observed 100 years ago, at which point people looked at this weird spectra and they said, this is some kind of main sequence star, it's got lots of metals in it, can't possibly be a white dwarf. But the temperature's all wrong, what is this? And then they kind of eventually they worked out that it was a white dwarf that had metals in its atmosphere. And so although at the time we didn't associate it with exoplanets, we actually had seen the first evidence for exoplanets already 100 years ago. And I added, there we go. I added in here as well, importantly, if we want to kind of think about actually the first planet detection was these planets which were around pulsars. So the remnants after much more massive stars have had a supernova. And those were the first planetary sized bodies that were detected. Cool. Okay. So hopefully, kind of if I've just to summarize where I've got to so far, hopefully I've persuaded you that white dwarfs do eat planets, and that planetary systems do orbit the faint remnants of stars like our sun, like white dwarfs, but they're really, really massive and really faint, far away from the star. But fortunately, occasionally they scatter some asteroids or comets inwards, and because the atmosphere of that white dwarf should have been totally clean, just pure hydrogen and helium, we're able to see the metals from those asteroids showing up in the atmosphere of that white dwarf. And from that, we can work out what the magnesium or the calcium or the aluminium or the iron content is of exoplanetary bodies, basically these asteroids or comets orbiting other stars. And so this is a really unique way to probe the composition of exoplanets. And so what if we're going to think about planets? Actually knowing what a planet is made from is really crucial. So I'm going to put up here the terrestrial planets in our solar system as a kind of cartoon. But if we want to know what it's like on Earth, and the fact that we're habitable, and the fact that we have land and oceans, plate tectonics and mountains and so on, we really need to know what our planet was made from and how that came to be. And doing that for exoplanets is really, really tough. And that's because those planets that we're talking about, they're really detected in ways that give us amazing information that those planets exist and that they're there. But actually, we are still relatively limited in what we can learn about the planets around stars that are kind of hundreds of light years away, where we haven't been able to kind of set a probe there or find out more information. So this was just to kind of illustrate the two main techniques that we use for detecting these kind of exoplanets. So we're sat here on Earth, and this is a star now. And because it's got a massive exoplanet here that's going around it, actually the star is going to go around the common center of mass of both that exoplanet star system. So instead of there being the star just sitting stationary, and we observe from Earth the star in the middle here, because the planet is going around it, actually the planet is gravitationally altering the pathway of that star, and that enables us to detect that there is a planet here. And when we do this, we're able to work out what the gravity is from that planet, and so we get the mass of the planet. It's called the radial velocity technique. And we can complement that mass if we're very, very lucky, and the planetary system aligns up perfectly, that when we look at it, the planet goes right in front of the star. Then when we observe the star for a very, very long time at very high precision, so this is kind of photometry, how bright the star is, it's a function of time, and we keep observing it. Eventually, when the planet's in front, there's a kind of dip because the planet's blocking some of the light from the star. And this is called a transit. And when that happens multiple times, we can confirm that there's truly a planet going around transiting that star. And what's neat about transits is that actually how much they block depends on the size, so their radius, essentially how big they are. It doesn't depend on how massive they are. And so putting this together, if we have both sets of observations, we can say, well, we know how massive the planet was and we know how big it was, therefore we know how dense it was. Can we use that to work out what it was made from? And the answer is yes. This is like the best that we can do, really, for working out what planets are made from. So this is a plot which is showing the mass of the exoplanet and the radius of the planet. And so basically it's telling us about its density. So Earth's down here, it's quite a dense planet, whereas say Neptune and Uranus are up here, which are kind of icy and much, much less dense. And so all of the black points on here are exoplanets that we've detected with error bars. And so we can kind of work out that we have some that are down here that are much more Earth-like. They sit on this kind of blue or purple curve that said that they're rocky planets, whereas there are some which are up here, much closer to the kind of Earth plus a massive hydrogen helium atmosphere. And so they may be, or closer to the water curve, that maybe they're less dense, and basically they're either ice giants or they're rocky planets with a massive atmosphere. But at the same time, you can see looking on here, like the error bars are very large, and it's really hard to work out exactly what the planet's made from. So if we look here, we've got a line for 100% iron and a line for Earth, which is mainly kind of silicate dominated planet. And you can see the difference between these two lines is very small compared to our error bars. And so actually, this is kind of where the white dwarfs come in, because they can tell us exactly what the bulk composition of those planets is, which elements make up those planets. And so this is a really nice plot from a piece of work by a colleague of mine, already almost 10 years ago now. And these are 10 white dwarfs where we got spectra from their atmospheres, and we were able to work out what the composition was of the asteroids that were in the atmospheres. And so these are all made into these little pie charts. And so don't worry too much, this is just some of the properties of the white dwarfs. So it's its surface gravity and its temperature. So that places these different white dwarfs. but actually what we care about is the pie chart on what makes up the exoplanetary material that's in the atmospheres of these. And so if we were to look over here, we can see that in green we've got iron, blue we've got oxygen, yellow we've got silicon, and red magnesium. And if we were to look at Earth, those are the major elements that make up most of our planet. There's a tiny little wedge here that's made up of all the other species like chromium, nickel, titanium, aluminium, everything else is this tiny little wedge. Most of the mass of our planet is made up of these 4 species. Whereas if we were to take a comet, you'll see that actually a comet is kind of half dust and half water. And so additionally, there's a lot more oxygen in blue and there's a lot of carbon as well. And what we see is that these white dwarfs in general seem to have accreted things that are broadly speaking rocky. They're broadly speaking asteroids like our own Earth, but between them there are strong variations in exactly how much they have. So for example, we have some which are very, very iron rich, like this one here, and number 10 there is incredibly iron rich, maybe something more like Mercury, whilst others seem to have lots and lots of oxygen, and we think maybe that's more related to the presence of water in the body. And so this plot was from 10 years ago. We're gradually kind of increasing the number of white dwarfs where we've been able to do this kind of analysis. And so we now have about over 20 objects where we've been able to analyze lots and lots of elements. And so this is a plot that we made recently. It's exactly the same as the last plot, except now we've just put the names of the white dwarfs down here and the mass fraction up here because we ran out of space to do a million little pie charts. And so the same thing, we've got Earth over here that's split between the major elements, and Comet Halley being much more oxygen and carbon rich than Earth. And what you can see is these kind of have all been ordered by how much oxygen they have in them. And we basically have huge variety in how much oxygen's been accreted by these bodies, as well as in how much iron, for example. And we can use those to really understand the kind of minerals that are forming these exoplanetary bodies. Yeah, and so we're able to do some really cool things as well, particularly with trace species. So for example, these are alkali metals, so things like lithium, sodium, potassium, and calcium. And this is a really nice piece of work that was done recently by a colleague of mine, Mark Collins. And again, we've got a spectra here with brightness against wavelength, and we're seeing different white dwarfs, and the lines show you where you've got you've got kind of spectral fingerprint of these different species. So here we're seeing very strong sodium, for example, in this object up here, and here there's strong calcium in all 3 of them. And so we can really learn about the kind of processes that might occur, for example, in the crust of our planet, which is very dominated with lithium and potassium. Yeah, and so that kind of brings me on to a kind of slight kind of change in tact, but I'm going to talk now about how we can use these observations really to probe even processes that are hard to understand on Earth. And so in particular for exoplanets, we can use these observations of white dwarfs to probe the geology of those systems. And so in order to kind of talk about that, I thought I'd start early in Earth's history. And so this is an artist's impression of maybe what our planet looked like 400 billion years ago, when the surface, we just finished forming and the surface was molten. So it's a magma ocean. And so this is prior to kind of forming the plates and cooling, that we could kind of have plate tectonics and everything we have today. What we think happened was that the entire planet melted. And why this is so important is if you have a rock that's totally molten and there's iron within that rock, that iron is much, much heavier than the silica within the rock. And so gravity means that those iron droplets will form within that kind of molten metallic liquid essentially and sink downwards. And it's that process of the sinking of the iron droplets that leads to the structure of our planet that we know today, where the iron forms this core in the middle and leaves behind this silicate mantle and a kind of cool crust on the outside. And this geological structure of our planet is absolutely key to so many of the kind of surface features like mountains and the existence of kind of even how much land we have versus ocean. It's all down to how we formed our crust. And what's kind of important to take away here is that there are particular elements that can tell us about this process of forming an iron core. And in particular, planetary cores are enhanced, we call them hydrophile elements. They're things like iron, also nickel, chromium, and those are things that sink to the core, whilst your mantle leaves behind the silicates, so elements like magnesium, silicon, and calcium, they will all have kind of stayed in your mantle. And what's kind of fun with this is that these are some of the elements that we can probe in the atmospheres of white dwarfs. And so we can use those spectra from those white dwarfs to kind of see what's going on in terms of the geology of these exoplanets and whether or not they formed cores. And what's kind of neat is that we find that some white dwarfs seem to have accreted things that are either fragments of a core of a body or they're fragments of the mantle of a body. And so this is really, really important because it shows us that that geological process of core formation is happening in other planetary systems. Okay, so bear with me, this plot is maybe slightly obscure, but we'll do our best. What you kind of want to take here basically is that we've got a load of elements along the bottom, and then we've got the ratio of those elements to magnesium, and it's normalized in a slightly bizarre way. And so these are the elements that we're detecting in the atmosphere of the white dwarf. And if we were kind of to take a straight line across here, we would get something like the composition of our sun or the composition of another star. And that's what we would expect to see in the atmosphere of the white dwarf, or we would expect to be the composition of the asteroid, for example. And instead, we see that this asteroid really didn't have very much nickel or iron. And those we just said were both things that went into the core of the asteroid. And so this white dwarf seems to have accreted something where the body formed a core, but that core material is not making it into the atmosphere of the white dwarf, and instead we're just seeing the mantle. And in fact, we can use this in detail to study exactly what the mantles were made from and the variety of different mantles that we have in other planetary systems. And even more excitingly, we even have some white dwarfs where they seem to have accreted a fragment of just the crust. So our planet Earth has a relatively thin crust. It's a very big planet, but smaller planetary bodies like Mars have much, much larger kind of lithospheres on their surface. And those lithospheres are enhanced in various things like sodium and calcium and aluminium and titanium. So the same kind of plots before. It's the elemental ratio to magnesium, normalized, and along the bottom are all the different elements. And this line would be a kind of neutral composition, so something like the sun. And instead we see this white dwarf accreted something which had lots of these crustal species and none of these things like nickel and iron and chromium that go into the core. And so this white dwarf seems to have accreted something where the body formed this core and a mantle and a crust. And at the moment, we're just observing the crust arriving in the atmosphere of that white dwarf. And so we can use all of these things to kind of probe many processes that happen during the kind of exoplanetary systems. And so I'm going to try and kind of tell a story now of how we can use these compositions to learn about the melting processes that lead to form cores, but also then what that tells us about when planet formation started to happen. Okay, so if we look at lots and lots of white dwarfs and we look at their spectra and we choose the ones where we can see evidence they've accreted some kind of asteroids, and we can kind of ask ourselves the question, well, how many of those white dwarfs accreted asteroids that were once molten, that had this phase where they underwent that large-scale melting that led to the formation of a core and a mantle? And we can look at that number by trying to understand the compositions of those cores and mantles. And so this plot shows the calcium to iron ratio in a big sample of about 200 white dwarfs as a function of the white dwarf temperature. And calcium to iron is a great way of telling us about this melting process of core formation, because calcium stays in your mantle while iron goes to your core. And so things that are down here on this plot, they're most likely to be core rich. They have very little iron. Sorry, is that the right one? Calcium. They have lots of iron. We've got a low calcium to iron ratio, so they have lots of iron. Whereas things up here would have very little iron, and so wouldn't be more likely to be mantle rich. And so in this study, we kind of performed an analysis of lots of bodies, and we found that a substantial portion of them showed some kind of evidence that they once had undergone melting. And so then we have to ask the question, well, these are asteroids. They're things that are quite small. What was it that heated up those planetary bodies? So our Earth is big enough that there was enough energy just from gathering all the material together to form Earth, just from the conversion of that gravitational potential energy into our planet, that was enough to melt it on its own. But these bodies are asteroids, and they're much, much smaller, and they don't have enough energy to melt just on their own. And so in our solar system, we have evidence that the melting was fueled by the decay of short-lived radioactive nuclides. So these are things like aluminium-26 that were incorporated into these planetary bodies early in their lifetimes, and they release heat when they decay, and that heat led to melting in our solar system. And we see that because we can observe the kind of decay products of this aluminium-26, things like 26 magnesium in solar system bodies, and we can trace back, therefore, how much aluminium-26 was added to these systems. But what's kind of interesting is that this process of turning aluminium-26, losing in basically a proton becomes a neutron and an electron, and out goes some energy, and we can heat it up. That only happens for 1 million years. So this is very unstable, and so it sits around, and then out goes my neutron, and that takes about 1 million years. And so that might seem like a long time for us sat here, but in terms of the kind of lifetime of stars and planetary bodies, that's actually a relatively short time period. And what that means is that if we want all these asteroids that were accreted by the white dwarfs to have enough aluminium-26, that was what melted them, that was what was their heat source, well, then they too needed to form within that first 1 million years of that planetary system. And so kind of to put that in context, Earth, for example, may be formed 100 or 200 million years after the birth of the solar system. So we're saying those first asteroids have to have formed within 1 million years. And so just to kind of summarize that, that's basically saying that because we see core or mantle-rich material in the atmospheres of white dwarfs, there's evidence that we needed to have some kind of heating, and that heating probably became from the decay of these radioactive nuclides, things like 26 aluminium, which only last for 1 million years. And so the fact that we see evidence of these molten bodies tells us that those bodies were forming early, that they were forming within the first 1 million years of the evolution of their planetary system. And so kind of let's to put that in context of how planets form. So if we think kind of back to the early stages of our solar system or any other planetary system, the birth of stars happens in these massive cool molecular clouds. They're tens of thousands of AU across, and they're very, very cool. Over densities in those clouds, so little kind of areas where there's a bit more material than elsewhere, they will collapse on themselves under their gravity. And that's when you start kind of star formation. So there'll be lots and lots of stars will form within this cloud. And these stars, they form by conserving angular momentum. So any kind of angular momentum within that disk, that within that cloud, means that the collapse doesn't go to a single point. Instead, it goes to a disk. And initially, these disks are big, and there's a lot of material moving through them. And they have these massive jets that throw out material. And they're shrouded in these kind of protostellar envelopes. They're really hard to observe. But these are where star formation is happening, and it's a really exciting process. Then, given enough time, so kind of on the order of 1 million years, these systems settle down into these kind of flat, thin disks, and these are what we call protoplanetary disks. And it's within those disks that really we're able to observe kind of the first ideas about planets forming, and the star now is already kind of still accreting more material, but it's almost fully formed. And it's from those disks that then we end up with a planetary system like our own solar system. And so this process is already complete within the first 1 million years of that planetary system. And so if the white dwarfs are telling us that the first planetary bodies formed within the first 1 million years, what they're telling us is that they were already forming over here in this first phases kind of concurrently with the star. And actually, this isn't the only evidence that's telling us that planet formation started early. There's an amazing radio telescope called ALMA, and it's revolutionizing our understanding of planet formation and these kind of early systems. And so this is a beautiful image of H.L. Tau, which is one of those early systems it's called a class 0 system, and it's still forming a star in the middle here. But what we see is these beautiful structures, these kind of rings here. And this was one of the surprising discoveries of ALMA in the last 5 years, was that these disks that we thought were just uniform disks actually have these amazing structures within them. And those structures are probably evidence that planet formation started already in these kind of star-forming systems, that things were really getting on and going really quite early. Yeah, and that's the same evidence that we have kind of from the white dwarfs. Right, cool. Okay, so just to kind of summarize, hopefully I've convinced you in the last half an hour or so that white dwarfs are really an exciting way to study the composition of exoplanets, and that planetary material in their atmospheres provides a unique way to get at what elements are present in planetary bodies, particularly around stars other than our sun. And from those white dwarfs, we find lots of evidence for geological processes in exoplanetary systems. So these kind of large-scale melting that leads to the formation of an iron core and a silicate mantle. And we can see that in the elemental abundances and the bodies that are accreted by these white dwarfs. And then I kind of finished off by talking about the fact that that melting needs a heat source, and it needs something to fuel it in kind of asteroidal-sized bodies. And in our solar system, we think that was aluminium-26, this short-lived radioactive nuclide that decays rapidly. And if that was the case, then this is really, really cool, because we're seeing around white dwarfs evidence that the first planetary building blocks really were forming early in their planetary systems within the first million years, and kind of concurrently with star formation. Yeah, so I thought I'd just leave you with this fun artist's impression that was made for me. It's of a kind of molten body. So one of these things that would have been kind of like our early Earth or an asteroid that's totally molten, the iron's sinking to form the core, and it's accreting onto a white dwarf. There's a slight kind of artistic license here, as in there is about 5 billion years of evolution that has to happen, and this thing cools and solidifies and sits in an asteroid belt and then gets kicked in and highly disrupted, but it's a very lovely picture. So thank you for your attention. Yeah.
Having the internet's planet, how long does it take to digest it?
Indeed. So that depends on how hot your white dwarf is. So young white dwarfs are quite hot and they have thin atmospheres, and then sometimes it can be days for it to digest it. But the coolest white dwarfs, they have much deeper atmospheres, and it takes millions of years for it to sink outside.
All suggests that the meals are relatively
Particularly the day ones. They're coming now, basically, astronomically speaking.
My other question is, you haven't really explained how the cross and mantle cores separate.
Yeah. Indeed, that's because we're not totally clear on that point. We have two theories. So on one side, if things form these cores and mantles in the asteroid belt, those asteroid belts are very collisional systems. And so they sat there for 5 billion years in the case of our solar system. There's a lot of time to have a lot of collisions that can chip off bits of mantle, and that can lead to kind of merging of your cores if you have very violent collisions. And so that process in itself is predicted theoretically to lead to a distribution of things, some of which have very large cores and some of which have very small cores. But we don't have any observational evidence that that really happens. On the other hand, a student of mine has just recently been working on an idea that actually it's a natural result of the process by which the material got into the atmosphere of the white dwarf. So the asteroid that was thrown in and shredded to pieces, it leads to this big disk, and within that kind of disk of material, the core material is on certain orbits compared to the mantle material, and so you end up with, as a function of time, you first accrete the core material and then later the non-mantle material.
I got one on two, but I was kind of why
Yeah, I should have said about that, yeah. So from days to millions of years, depending on the temperature of the star.
Well, a question
Mm.
is maybe, is there a bias from terrestrial white planet white reference to those white
Rather than comets, or rather than
like gas giants like that? That's rich.
yes, okay, well, so there are one or two white dwarfs which seem to agree to something that is really, really volatile rich, and it has been claimed it maybe is a gas giant. I think the mechanisms, it's very easy to scatter asteroids everywhere by a big planet. Whereas if you want to scatter a planet onto a white dwarf, you need to have something bigger than it, basically, it's that system. And so there aren't that many planetary systems, statistically speaking.